Have you ever heard anyone talk about the Van Allen belts? Well, that was a study made in 1957 trying to give a vague idea as to the radiation belts surrounding the Earth. However, it was a vague idea that they created and kind of gave a visual of two donut-shaped rings that were coming out of the top and the bottom of the Earth and kind of surrounding the Earth itself. That was in 1957. Did you know it's 2019? That is not an applicable term in 2019. Now we call it the magnetosphere. And did you know that the magnetosphere has hundreds of bands? We just have dozens of names for regions of those bands because of the hundreds of different bands just within those regions. It's no longer the Van Allen belts. And so, if you ever hear someone say to you, we landed on the moon, and then they talk about, oh, you think that we couldn't fly through the Van Allen belts? Well, I'm going to point out exactly how nonsensical that is, everything they're saying. Because it's not 1957 anymore, and science has shown that it's not a matter of flying through the belts. So, here in this graphic, brought to by NASA, this is a picture of what space represents. Now, first thing I want to point out is there is not one single graphic that NASA has ever created or an artist has ever rendered that represents the magnetosphere in its entirety. Every band, every layer, and then as well the atmosphere and the ionosphere that happen to be within the magnetospheric bands. Not only that, you'll never find one that's to scale, period. You will only see variations of different types of models of magnetospheres. Some will show the Van Allen belts and the fuzz, and some will show hundreds of different bands coming out of the tops and bottoms. Some will show great different fields of areas like plasmaspheres and magnetosheaths, all confined within the bow shock, but none of them will actually show everything, and they'll never be to scale. If the Earth is 6,000 miles in circumference to that picture, then there will not be 25,000 miles away where the bow shock is. It's just never accurate and never to scale. They've done this intentionally. Now, this graphic right here I wanted to use because it represents the most consistent thing we disregard, and that is a solar energetic particle's consistent light and mass that does not make it through the bow shock. Everything the magnetosphere does is take 99% of all of energy and mass and move it away from the Earth. We never even, our Van Allen belts don't even receive any of this energy or mass. So 99% of the energy and mass that is in the Van Allen belts is outside and never enters the bow shock of the magnetosphere. So when someone tells you it's just a matter of flying through the Van Allen belts very quickly, that's just 1% of the 100% of the mass they say they're flying through. Now, if it's a big deal to be within that 1% of that mass, now the MMS missions have shown that electromagnetic reconnection points cause plasma that is heavy turbulence and more radiant than found within the thermosphere, but definitely more radiant in the plasmasphere. And so with these studies, we found that it's not that it's greater than outside of the magnetosphere, it's just as great as outside of the magnetosphere. So while there's only 1% of the mass and energy, that 1% is as great as what's outside of the magnetosphere's bow shock. So if you were to fly through the Van Allen belts very quickly, you're just flying through that 1% of the 100% you're about to fly into. So it's not a matter of time and how long it takes you to fly through, because if you're spending a great deal of time outside of that, in lunar transit per se, you're going to end up being ionized by 100% of the mass that is the power, that is the 1% you're saying is a problem. Therefore, this is the most accurate representation. However, if you were to actually make one, you would just see a black dot within a sea of white light, because every single cubic meter of space is filled with particles and energy, and all of that is moving at the speed of light and moving mass at the speed of light around us. We're not like Mars because of all of this magnetosphere and all of the magnetospheric bands that keep us safe, which also keeps 1%, and that allows that 1% to keep enough radiant energy to create the film that we call life. And so the electromagnetic fields that Mars doesn't have is why Mars isn't like us. We aren't like Mars because the magnetosphere shields 99% of the electricity and mass from the actual planet's atmosphere, and so we can have an atmosphere. So when you hear someone say we just need to fly out real quick, keep in mind we're only 230 miles up, not 25,000 miles out where this bow shock right here starts and turns everything away. It's within 1% of the 1% that is 100% of outside. Why? Because when it hits the bow shock and that 1% makes it through, the 1% is filtered through electromagnetic reconnection points from the magnetosheath and through the neutral point of the tail, through polar cusps that come down through various bands that eventually make their way into a field called the plasmasphere, and the plasmasphere eventually starts radiating that within the ionosphere, which comes through our exosphere at about 6,213 miles or so, and then that is when that, from the 1% that made it through, we get 1% of this 1% that is filtered from the plasmasphere and the magnetosheath and the actual magnetosphere down into the upper atmospheric layers. And so when it hits the ionosphere and travels down the polar cusps and starts hitting the exosphere and then makes it through the exosphere into the upper thermosphere, well, by that point in time, that 1% is much, much smaller. If you watch anything about cosmic background radiation particles and how they hit our atmospheric areas and layers, they fracture, and so they become less. And why is this? Because they're starting to come into what they call, in the upper thermosphere, the same amount of atmosphere pressure and density as Mars, which is 0.01%. So there are still some molecules remaining that have made it up from the mesosphere, which is under the thermosphere. And so those molecules, as they make their way up, they're hitting and they're fragmenting these rare particles now. And they're very rare at this point, 1% of 1%. So as they start to come down and filter their way into what is now the lower thermosphere, where the International Space Station is at 230 miles up, now we're starting to make it to where, there's so very few of them that if we use certain mass like transitional or passive shielding metals, we can use at that stage, not any higher, but right there, we can use those metals to break up the remaining 1% of the 1%'s charge into that, and we don't absorb it, the crafts do, and so we just get some treatment and we're fine. However, it still, if it misses us, it keeps going through. This is where space weather and Earth weather come together to make climate change. One of the reasons why there's the biggest climate change battles is the 1% of the 1% that keeps us alive also is ever changing and altering the structure of the mesosphere. So first we talked about in the 90s the ozone depletion. Well, that was a part of our mesosphere. That's where all of those heavy ionized particles, the 1% of the 1%, starts to make it down. Well, right there, as it starts to make it down to that point, all of those molecules are destroyed by the free radicals. It's like taking a big marble and launching it into a pile of little marbles. It just breaks everything up. And sometimes it fractures, but most of the time it just relocates all of the atomic structures to different molecules. Some float up, some come back down. And that's where they're talking about the new ICON mission and understanding, what the space radiation is doing to our atmospheric densities, how much we're playing in with that, but mostly just how much does it affect our weather, whether or not we do anything to it or not. So all of the reconnection points that are above cause all of that, the 1% of the 1% to rain down and create aurora borealis, things that we all understand and can acknowledge, which is nothing more than space weather meeting our weather. Now, we've acknowledged from Sprite's existence that just like lightning goes down, electricity and lightning go up because positive negative charge exists on both. And while that happens, we also are losing a majority of our oxygen and helium and hydrogen and all of our base elements. However, we're still retaining most of our carbon and our nitrogen and all of these elements that will eventually create a Venus-type planet, which is another reason why we're not talking about Venus, we're talking about Mars. Is we want to talk about what potentially could be if Mars had a magnetosphere and started, have expansion exist. It will eventually become the Goldilocks zone as the sun gets bigger, and therefore it will be a habitable place. We don't talk about Venus because Venus was like Earth. This space weather caused its atmosphere to become what it is, as we are becoming that, whether or not we stop using cars or all of that shit or not. Granted, our life quality will be better if we quit. Obviously, it's better to have oxygen than carbon dioxide, but So if you ever hear anybody talk about the Van Allen belts and you hear them say something like, oh, you think that, Apollo couldn't have gone through the Van Allen belts, or it's too radiant just within the belts, remind them that there's 99% of the mass outside of the belts that inside of the belts has never encountered, because it only gets 1%, because that's the purpose and the function of the bow shock and why Earth and Mars are different. That's it. The end. And we're not leaving Earth's magnetosphere without a magnetosphere on our crafts. It says Princeton, Berkeley, and UCLA, and GSI, and CERN, and every single particle physicist on the planet, every solar physicist on the planet, everything from NASA heliophysics, and everything from all of our international partners. The end.